All right, let us wrap up some final thoughts on gravity and then get into the next subject that we're going to think about, which is oscillations, thinking about oscillatory motion. There were a few things, so let's recap what we've done so far with gravity. We were able to write down a general form for gravity. Gravitational forces as a result of Isaac Newton, written down the way that Isaac Newton wrote it down, is that you need two masses, and if you have two non-zero masses, they exert a tug on one another. That is equal and opposite in direction, and the magnitude of that tug is given by some constant, big G, which you can always look up, the product of the two masses, divided by the inverse square of the distance between them. So, like we've been seeing in the handout that we did in class, the result of this is, for example, an object that is twice as far away exerts 1/4 the gravitational force because the denominator, that r, increases by a factor of 2, but since it's being squared, the overall amount of force goes down by a factor of 4. The direction of this force occurs in the line connecting the two objects. I'm guessing in those drawings I'm using D, so I'll make this a D. For point particles, you can think of it as just the distance between the 2 points. For spherical objects like stars and planets and moons and whatnot, you can treat it as if you're drawing a line between the centers of the two objects and calculate the gravitational force as if it was acting solely at the center. This makes the assumption, because it's by making the assumption of spherical symmetry, you're allowed to do this. This is not a center of mass type argument. If it was a weirdly distributed thing that wasn't perfectly spherical or spherically symmetric, the gravitational tugs would be uneven, and as a result, there might be something like a torque or something that exerts on the system from gravity. Which is why when I said before in rotation, when we were talking about gravitational torque, I said just assume it's at the center of mass. I have also said along with that, that's only true when the gravitational field is uniform. So when you're near the surface of the Earth, you can assume gravity is acting at the center of mass. If the gravitational field is not uniform, like in this case, where it depends on the distance squared between the two objects, which means that, for example, if you don't have spherical symmetry, like this part is being pulled more towards M2 compared to this part. One side of the object is closer than the other side. This actually is the reason why we get things like tides, but that's a different story. But for spherically symmetric objects, you can always assume, you can treat them as if they're point particles with all their mass concentrated at the center of the object. And then one of the other things we showed we were able to derive for uniform circular motion is a version of Kepler's third law, which says that the period of the object as it orbits around another object, so you might have the sun, you might have the Earth going around. It's going around in a circular orbit a distance r away. The mass of the sun might have some mass big M. And the amount of time it takes to go around once we call the period. The relationship between those three quantities is given by Kepler's third law, which we derive for uniform circular motion, where the big object in the middle is at rest. Let me just quickly recap what Kepler's laws are. We've proven, in a sense, one of them. Another one is, there are 3 laws in total. Kepler's first law was saying that objects in the solar system orbit around the sun in ellipses, so oval shapes. It turns out for the solar system, most of the orbits are very close to being circles. A circle is actually just a special case of an ellipse. An ellipse is a more general object. Proving Kepler's first law is doable, but it's a little involved. So I put a handout on Moodle if you're curious on how you might go about showing Kepler's first law. In general, it actually turns out, if you ever wondered where these conic sections and why conic sections mattered in high school, actually it turns out that you can show with an inverse square law like gravity. An object that's orbiting another object can only have one of 4 orbits. The orbit is either a circle, an ellipse, a parabola, or a hyperbola. Two of those obviously are one-way trips. Two of those means the object never comes back once it goes along, one of the paths. But for the circle and the ellipse, those are stable orbits that repeat themselves over and over and over again. Kepler's second law, we will prove today, is more or less just a statement of the conservation of angular momentum. What it says is that a way of thinking about this is it says an object moves faster when it's closer to the sun and slower when it's farther away, such that geometrically all those purple wedges have the same amount of area within them. If I were to calculate the area of those wedges, they would all have exactly the same amount of area. We'll show that this is just a result of angular momentum conservation. And this is also the reason, for example, why comets spend very little time near the sun. Halley's Comet comes around once every century, roughly, but spends most of its time way out in the farthest reaches in the solar system, and quickly whizzes by the sun once every 90 years or so. Then the third one was Kepler's third law, which says that the period is not just related to the cube of the semi-major axis, or the radius of the orbit, but it's that the period squared is related to the cube of the semi-major axis. Another way of thinking about this, if you were to take the square root of both sides, this would be saying, essentially what that says is that the period squared is proportional to the radius of the orbit cubed. That's equivalent to saying that the period is proportional to the radius of the orbit to the 3/2 power. And what's interesting is that 3/2 is bigger than 1. It's not just that you double the orbit and therefore double the circumference, you have twice the distance to travel. You might think then it might take twice as long. But that's not true, because if you also double the size of the orbit, you are twice as far away from the object. Gravity is weaker. Gravity in that case is 1/4 as strong, and that gravitational tug results in the object also moving slower. So it not only has more distance to cover, it also moves slower as a result. In the handouts, the in-class handouts, we show that the velocity of an object that goes around the sun, for example, goes as the square root of gm, the mass of the sun, over r squared. So you could say that the period should go roughly as the distance it has to travel, which might be something like 2 pi r, and then divided by the velocity that it's going around that circle. And I'm dropping 2's and pi's and numbers, and I don't care about numbers. But the numerator scales as r, the denominator scales as gm over r. Again, I don't really care about numbers, so I'm just looking at the radius. So this is the same thing as r times the square root of r, with some numbers that am ignoring for right now, or that r goes as goes to the 3/2 power. Not only do you have more distance to cover, but you're moving slower as a result. And what makes universal gravity even more meaningful and interesting is that it's universal. So not only can we use it to understand how the Earth goes around the sun, or how the moon goes around the Earth, or why apples fall to the ground when I release them, but it also can explain why moons orbit around Jupiter, why Jupiter orbits around the sun. All of this can be explained with the same one law of universal gravity. In this case, you see 2 of Jupiter's moons also orbiting around Jupiter as it rotates. You actually see a double solar eclipse. You can see the shadows that's being cast by, in this case, the first moon, and then there's another shadow that's being cast by a second moon that's a little bit farther away. But notice that, and so they would be seeing a solar eclipse where that shadow is, would look right there. They perfectly overlap with one another. So you see a double solar eclipse at that point. Anyway. And it also can explain things like binary stars, why the sun orbits around the center of the galaxy, and can be used to explain a whole wide variety of phenomena with the same law of universal gravitation. The generalization of this is a very powerful technique. Anything that can be generalized to apply to a whole variety of subjects has much more, I think, intellectual power than a formula that only works really for a very, very, very specific thing. So like in the case of this example, these are showing examples of, say, Kepler's laws which are also obeyed. But in this case, it might be cases where the objects are very similar size. The one on the bottom is closer to, say, like the Sun and Jupiter, where the Sun tugs on Jupiter and causes Jupiter to orbit around the Sun. But by Newton's third law, Jupiter also tugs on the Sun. And so the Sun ends up wobbling a little bit. When we say that the planets go around the Sun, really that's imprecise. What we should be saying is that the planets and the Sun all orbit their common center of mass, which, since most of the mass in the solar system is in the Sun, the center of the mass for the solar system is roughly, if not always, inside the Sun. And the Sun just wobbles around in place. I think if you have all the planets aligned perfectly in a line, you can pull the center of mass out of the Sun. But since that's not how the planets are, generally the center of mass is always located, within the radius of the Sun. But if you have, say, Pluto and Charon, which are two objects that are roughly equal mass, or something like these two stars that are kind of on these weird eccentric orbits, which again, notice they move faster when they're closer to one another and slower when they're farther away. These are all cases that can also be explained by the same universal law of gravity. And as a result, they all also obey a Kepler's set of laws, even though Kepler himself came up with these laws to explain the planets going around the Sun. But nonetheless, they are actually a general set of laws that are true for any two bodies orbiting one another. Right, so we'll never need to make use of this fact, but if you're curious, the real way to write down Kepler's third law is to not just write the mass of the really big object in the denominator, but to write it as the sum of the two masses. This is technically the true answer. The approximation of replacing it with just the central mass is because usually the central mass, the Sun, for example, is much, much bigger than the other object that's orbiting around it. The Sun appears to be stationary while the Earth goes around the Sun. The mass of the Sun is much, much greater than the mass of the Earth, so that denominator term is to a very good approximation, just the mass of the central object. And again, this is how we actually measure things like masses of planets and stars. I know the period of the Earth as it goes around the Sun. I can look at the stars to determine, when I'm seeing things repeat themselves. I can triangulate my location with Venus and Mercury, and I can use that to get the Earth's distance from the Sun. Then if I know P and R, I can solve for the mass of the Sun as a result. You could do the same thing with monitoring the moons of Jupiter. All right, so what I wanted to do was just kind of wrap up. So we talked about forces due to gravity. I wanted to do a little bit on energy and angular momentum due to gravity. Before, we had said something like that gravity was a conservative force and it had some potential energy that looked like, mgh or something like that. And I would say that this is not true in general. It is only true if you happen to be near the surface of the Earth, because little g assumes that you are near the surface of the Earth, and it's only the Earth's gravitational pull that you're worrying about. But what if I had an object, had some big at mass m, and we had some object over here, I had another mass m, there's a line that connects the two, and they perhaps start a distance d naught away, and d naught might be light years, for example. They will exert gravitational pulls on one another, and they will eventually, they might get to a position where they are very close to one another. And as a result of the gravitational pulls, they might each have very large velocities as a result, as they fall inward towards one another. What can we say about the energy of the system, when we think about things like this? Is gravity still a conservative force when you're dealing with the universal version of gravity and not assuming that you're really, really close to the center of the Earth? Or sorry, to the surface of the Earth. If you're really close to the center of the Earth, you have other issues. So let's take this example, and let's calculate the work that's done by this universal gravitational force. So work is, of course, done, and let's focus on, say, the work done on the right object from the left object. So it's feeling a gravitational force acting on it, which is pulling it and making it move across some distance. If everything is set up in a nice horizontal line, then everything is going to move in a straight line as a result. So if I go back up to this drawing, it feels a gravitational force that's pulling it towards the left, and then it, as a result, starts moving towards the left. So the force of gravity and the direction of displacement are parallel to one another. Thinking back to work, remember that just meant that this was just the magnitude of the gravitational force times the overall displacement, where I am starting a distance d naught away and I'm ending a distance r away, where r is assumed to be, I guess it doesn't have to be much less, but just r is assumed to be less than d naught. The magnitude of the gravitational force is this gmm over r squared dr. That's not too bad. The g and the m's are constants, so they can come out of the integral. And I'm concerned more now with evaluating integral of dr over r squared, which once you do enough integrals, that's pretty straightforward. So the power raises up, so this becomes 1 over r, evaluated from d naught to r. So this then becomes g big M little m, and then it's 1 over r minus 1 over d naught as a result. I did a couple steps there, so you can fill in the blanks. Now if I look at this, and I say, well, r is less than d naught, which means that 1 over r is greater than 1 over d naught. The work done by gravity in this case of gm little m, 1 over r minus 1 over d naught, is positive as a result, because that first term is bigger than the second term. In this case, the work is positive, which means the kinetic energy, of course, is the change in kinetic energy is positive, which should not be too surprising. You can go through the same analysis of determining whether or not this is a conservative force, and you arrive at the conclusion that it still is a conservative force. What you get is that it is still path independent. Remember, what does it mean to be a conservative force? It means that you can take any path to get from point A to point B, and it does not depend on which path you take. The overall total work that occurs over that path is exactly the same no matter what the path is. Your book also sketches it out a little bit for you as well, but we're just going to take that as a given. That means, if gravity is conservative, we can write a gravitational potential energy for gravity. In this case, we just showed, remember, we defined a change in potential energy as minus the work that was done. So what we actually just showed is, in this case, there was a change of potential energy that is something that like this, which is some negative number. Remember, the idea is that if you cash in your savings and cash in your gravitational potential energy, it goes down and your kinetic energy goes up as a result. From it being very separated to very close. If I were to plot total energy, in this case, there might be very little kinetic, but very high potential. And then as they come together, they start moving. And there might be less potential as a result. might be a way of thinking about this. But I'm going to erase that because that might be a little confusing with what I'm about to do. Here's where it gets a little tricky. So remember when we had potential energies in chapter whatever, we could talk about how it was only the change in potential energy that mattered. What I've written down here is exact and correct. But when we wrote down something like U equals mgh or U equals 1/2 kx squared, we were making an assumption about where the 0 point was. We were making a decision about where 0 was in our coordinate system. We said in that case, the floor was, or the ground where the height is 0. We called that, where there was no gravitational potential energy. We could have called somewhere else, the 0 point. And then at some points, maybe gravitational potential energy would have been negative. Right, for gmm over r squared, the convention is that we take the 0 point, u sub g, to be 0 at infinity. And the reason we do this is if you have two objects that are separated by a distance, which could be incredibly large, they nonetheless still exert a gravitational force on one another. The Milky Way is feeling a force from the Andromeda Galaxy, even though it is millions of light years away. That force gets weaker as you get farther away, so the idea is that gravity essentially goes to 0 asymptotically as you get farther and farther away, as the objects get farther and farther away from each other. So we take the convention that there's no potential for gravity to do anything, and we call that the 0 point. So we define the potential to be 0 way off at infinity. So in what we did above, that was the convention of taking that d naught, goes to infinity. Imagine separating the two objects slowly but surely, more and more and more. And then that allows us to write down a gravitational potential energy as G m1 m2 over r, where r is the distance between the two objects. I think that's worth a highlight. So essentially we've come up with a more general version of potential energy for gravity. This actually you can show mathematically, this becomes mgh if you're near the surface of the Earth and you make the appropriate mathematical approximations. You can show this is identically equal to mgh. But in general, we define the potential energy as negative g m1 m2 over r, the distance between them. So, for example, suppose I have, a particle m, and it's separated by a distance d naught between another particle m. Then after some time, they become a distance, say, d naught over 10 away from each other. And suppose they were released from rest. What are the final velocities that both of these objects ultimately have when they are a tenth of a distance away from one another? So in this case, if I identify my system as the two particles, then I can say, as a result, that there is no net external force on the system, right? There's only conservative forces. I could say then that the total energy is conserved. That idea has not changed. So I could write down t plus u, when they're separated by a distance d naught, that must equal t plus u Now be careful here. So it's the total. Remember, this is the total overall final for the entire system. So what that actually means, the original for the entire system was the kinetic energy of the left particle, the kinetic energy of the right particle, and then there's a potential energy between the two. They don't each have a potential energy because they are pulling on each other. So when we think of something, when we say the potential energy is negative GMM over R, that is a potential energy for a pair of objects that are pulling on one another. You would not say they each have their own potential energy, but there's a potential energy associated with them as a pair. They could get closer, they get farther away. As a result, gravity has to do work when it does that. And then that equals the final kinetic energies plus the final potential energy between them. I don't know why I'm in blue. So if they're released from rest, this is 0, this is 0. And they're the same mass, so it's m squared. They're initially a distance d naught away from one another. So I could write the total energy as 0 plus minus gm squared over d naught. And then that equals, the left particle is going to be moving with some velocity. The right particle, by symmetry, is going to have the same, they're the same mass. As a result, by the symmetry of the system, they are going to have the same kinetic energy, minus gm squared over, then looks like it's d naught divided by 10 in the denominator. So let's see, how does this simplify? I can move the gm squared, I guess that's 10 d naught minus gm squared over d naught to that side. The 1/2s add together, and this just becomes mv squared. It's kind of nice. One of the m's cancel, so these become just 1. That goes away entirely. I could factor out, looks like I could factor out gm over d naught. And then this is just 10 minus 1. Or 9 gm over d naught equals v squared. Or v equals, looks like 3 root gm over d naught. You could actually find the velocity of the individual objects once they've come to a distance that's 10% its original distance. Which is pretty nice, because this would have been a very hard integral to do if you wanted to do forces directly, if you wanted to do F equals ma directly. This also gets us into the idea of escape velocity. Let me go back to the Earth. And suppose I have a ball that's some height h off the surface. I could ask, what is the total energy of the system with regard to the universal law of gravitation? For the ball. For the ball's total energy, right, it could have some kinetic energy. Realize I used T up above. I'm sorry about that. Different class uses T, not K. Sorry. That was supposed to be kinetic energy. Kinetic plus there is some potential energy between the ball and the Earth. So in this case, if, say, it is moving at some velocity v, we can stick with 1d for now. If it's moving with some velocity v, this is 1/2 mv squared minus g m Earth m divided by, not h, but is the distance between center to center. So this is something like r Earth plus h, or something like that, for the potential energy. Got to be careful, because you might think it's gmm over r squared. That's a force. Gmm over r, or gmm over some distance, is potential energy. So I could write this as the total energy of my system. And I could ask, what is the minimum velocity I have to throw this ball away from the Earth such that it never comes back? We call that the escape velocity. So what is V such that, I guess in this sense, h goes to infinity? That it is perfectly okay for h to get larger and larger and larger, and I don't have to worry about the object coming back. Right? I can say this is h final. If it starts at a height h initial. So we could think about this problem, and if I think of the system as just the ball, there is an external force, but it's conservative. In this case, I'm free to actually say that, again, energy is conserved in this case. There is an exchange between the potential energy between the Earth and the ball and the kinetic energy that they both have. In this case, let's focus on the kinetic energy of the ball. I'm treating the Earth as kind of remaining stationary, which is a okay approximation here. I could treat the Earth as also being allowed to move, but the answer is not going to be that different here. Actually, be very minuscule if it's really the mass of a ball. So in this case, what I'm saying is I want to ask for the ball, what is the total energy at launch, a height h naught above the surface, and then that must equal the total energy at infinity. And if I'm thinking of the escape velocity, I'm thinking that, what does it mean to just barely escape? It means that as I get farther and farther away, one, I don't at some point stop and turn around and start to fall backwards. That is the case where, for a ball, I do not throw this ball at the escape velocity, right? Eventually, it does not have enough kinetic energy to escape the Earth. It goes up, and the Earth eventually, the gravitational pull of the Earth wins, and it eventually falls back down. But launching a rocket ship, it leaves the Earth's surface, and gravity does not pull it back down to the Earth. So it achieves escape velocity for the Earth. So how do you actually calculate that? So the total energy initially was 1/2 mv squared, and then there was some potential energy, gm Earth, m ball. And I'm going to write this actually as just the radius of the Earth. I'm assuming if the ball is starting very close to the surface, like if I'm throwing it up, that little h is so tiny compared to the radius of the Earth, it doesn't really matter. So here I assume the initial height is much, much smaller than the radius of the Earth. Again, a perfectly fine approximation, a completely accurate approximation if it's a rocket that is launching off the ground. And then if I just barely make it to infinity, as the ball is moving away from the Earth, it is constantly slowing down. It is constantly moving slower as it travels away from the Earth because the Earth's gravity is continuously pulling back on it, trying to make the ball return to the Earth. But it never quite gets to zero, and it never quite is able to turn around, except perhaps if you let it go all the way out to infinity. So you might think that the bare minimum that is necessary for the ball to reach the edge of the universe, which we'll call infinity, is that it reaches that point with essentially no kinetic energy. It slows down, it continues to slow down, it keeps slowing down. Gravity never lets go. It keeps slowing down as the ball gets farther and farther away, and it only finally comes to rest way out at infinity, where the gravitational force has essentially gone to zero in that case. In that case, the gravitational potential energy is also zero. That's where we defined zero to be. Which means that the energy at that point, that final point, is zero. The total energy is zero. So then this says, if we're looking for what is this escape velocity, that is the result of solving this expression. What is the value of v such that this difference is identically zero? Then you can see the mass of the object or the ball or the rocket cancels, and it looks like v escape is square root of 2 g m Earth over r Earth, which for the Earth is about 11.2 kilometers per second. I'm not going to do this. I'm not going to do mental math in my head. About 25,000 miles per hour. If you get up to that escape velocity, you are safe to know that you're not coming back. Also note what this says is that what is the, if you were to look at this, what is the total energy for an object that does not escape the Earth? In that case, it eventually turns back around. It could potentially start at the same point. I could say start the ball at the surface of the Earth and throw it upward with some velocity. Its total energy is then still 1/2 mv squared minus g m Earth over r Earth. But if I didn't throw it fast enough so that it doesn't escape, that means, if there's no escape, then that means v is less than v escape. But if you think that we derived v escape for when this expression equals 0, that implies that if you add up this expression and you get something that's negative, that implies you're gravitationally bound, that you cannot escape. You don't have the escape velocity to escape from the object itself. The ball will not leave the Earth. It will eventually turn around sooner or later. This is actually the criterion for what makes a binary star system. If you have two stars and you want to orbit and you want to see, are these two stars orbiting each other? Or are they looping around each other? Or are they just passing in the night? The way you would figure that out is you would calculate the total energy of the two stars. They both have kinetic energy. They both have a gravitational potential energy that combines the two. And if the total energy is negative, we would call it a binary star system. That is essentially the criterion I use when I do a simulation and try to determine what stars in my simulation are binaries and which aren't. All right, so not to say that this class doesn't teach you something that has real utility. Let's think now about Kepler's second law. Suppose, and I drew this with a very eccentric orbit, even though most of the orbits in the solar system do not look like this. So I have some planet that is going around a star, and perhaps the planet is located right there. And it is moving with some velocity v at that point. It is connected to the star in a line that's drawn like this. And you can think of that the star serves as the axis of rotation. It is the point that the object is rotating around. It's not rotating in a circle, but it's rotating nonetheless around the star. There is a gravitational force that pulls along that direction, but that direction is also the direction of the moment arm that connects the axis of rotation to the planet. So in this case, the sine of the angle in this case is the sine of 180, which is 0. So the torque as a result of the gravitational force from the sun on the planet is 0. There is no torque that is acting on the planet as it goes around the star in this simple little solar system where it's just the one planet and the one star. Even with the other planets, it really, they don't really influence anything because the sun is where most of the mass is. It's the dominant thing in town. This implies that the angular momentum is constant, particularly for the planet. If we're keeping the sun as stationary at the axis of rotation, then the angular momentum for the planet is constant. It does not change. So let's see. So we could look at the angular momentum, which is r cross p, the momentum of the planet as it goes around the sun. This is the same thing as m r v sine of theta. Momentum is just mv. R is this distance. This drawing is getting kind of busy. Let me redraw. I'll put the planet out here. This is some distance r. It's moving with some velocity v, or similarly it has some momentum p. There is some angle between them, and it's not always a 90-degree angle like it is for circular motion. Circular motion is always perfectly 90 degrees. For an ellipse, it's not always perfectly 90 degrees. But I can interpret this geometrically and think, what is v sine of theta if theta is this angle right here? Remember that we talked about, for both the cross product and the dot product, we talked about, like, for the dot product, you had two vectors. You had two vectors, and the dot product gave you the projection of one vector on the other. You got the parallel component from the dot product. The cross product gives you the perpendicular component. There's some component of this vector that is perpendicular to the purple pencil. This component right here. The cross product helps get you that component. So if we look at what v sine theta is in this case, this could be written as just mrv perpendicular, where this is the velocity perpendicular to r. If this were perfectly circular motion, then this would just be the full velocity. But really what this is, you can imagine a hypothetical circle here, that it has a radius going around, r, that goes around the sun. And what this is saying is that there's some velocity component v, v perpendicular, that is the perpendicular component that is not parallel to r, but is perpendicular to r in this case. The planet has both, but this is a way of pulling and extracting out the component that's perpendicular. Why that's helpful is because then we can imagine we can use our relationships for linear variables. That if we were to assign an angular velocity for the planet, an angular velocity, we said, the velocity as you go in a circle is the radius of the circle times the angular velocity, which in this case is the v perpendicular component. So I could write this as m omega r squared. I replace v perpendicular is just omega times little r. It's a crappy v. There we go. For some angular velocity as it goes around the star, in this hypothetical circle. You might think it's unclear how this has helped us at all. We will see, because this has given us a way to write down the magnitude of the angular momentum in terms of other quantities, which we are about to see is going to play a role. Now for this hypothetical elliptical orbit, suppose I have a planet that's here, and then at some time later it's moved out to here. And I'm admittedly grossly exaggerating how, what this would look like. Really, what you would do is you would do this as in the calculus sense, where you would look at 2 points in time very, very close to one another. But just to help you kind of imagine what this looks like, I'll consider 2 points in time that are kind of fairly widely separated. But you can imagine doing this in the limit of very small delta t. This has some area A, which we could write down by approximating this as a triangle that has some height and some base. Saying that the area is 1/2 base times the height of this triangle. So the base and the height, if you think of this as a very infinitesimally, amount of time where the 2 points on the orbit are actually ridiculously close to one another, it's essentially like I'm drawing, 2 parallel lines. So the height of the triangle, or essentially I have a triangle that looks like this, where this is the height. But you can imagine if I look at 2 points ridiculously close in time, the triangle actually looks more, like this, say, where the sides of the triangle and the height of the triangle are essentially the same. And then the base is essentially given by the arc that is swept out by the planet as it moves along this elliptical orbit. So I could write this as 1/2 r times some change in theta times the height, which I'm going to approximate as r, which I've been using little r, so let me rewrite that. 1/2 r d theta times r, base times height. This is essentially r d theta. The height of the rectangle is essentially the same as the line connecting the 2 points r. And in the calculus limit, this is actually pretty good. So then I might say, to keep this in the calculus language, I might say this very small amount of area, which I might say is dA, this little piece of area that's been swept out, between 0 and 1 picosecond, is 1/2 r squared d theta. For some angle, I guess I could define theta, for some angle theta, that it has moved around the star. D theta is just omega dt. If there's some omega that it's moving around the star with some angular velocity, we can write d theta as just omega dt. This essentially was how we defined omega. I'm just going backwards. So I can write that the area that's swept out in a given amount of time is 1/2 r squared omega. Kepler's second law claimed that it was equal areas and equal times. Kepler claimed that this derivative is a constant. Though it's clear that r is changing, it's clear that omega is changing because it's not moving in a perfect circle in this case. It might speed up when it gets closer to the star. We actually have seen that up above by angular momentum conservation. Going back up to angular momentum conservation, it's saying that L is a constant, which is m omega r squared, which means that if r goes down, if you get closer to the star, to keep this a constant, omega must go up. You start rotating around the star faster in order for this overall expression to remain a constant, assuming also the mass of the planet is not changing. But now we're going to use this. If L of m omega r squared is a constant, and I'll write it, as a constant, it's like a script L. Then notice this constant angular momentum divided by m is omega r squared. The left-hand side is a constant. We said the angular momentum is a constant, so L is a constant, m is a constant, and that's equal to omega r squared. But lo and behold, that is exactly what is written here, so I could replace this with 1/2 angular momentum divided by m, which is indeed, all of that is a constant. So the amount of area that's being swept out every dt is a constant, no matter if you're close to the star or far away from the star in the orbit. That's the whole idea with equal areas in equal times. Really, I think the more useful version of this is something like this, where it's saying that the closer you are to the object, the faster you move. Oh dear. All right. I like gravity too much. These 3 lectures took longer than I wanted them to. That's okay. I can lay the groundwork for oscillations and then get into more of the math stuff later. All right, so leaving gravity, now coming back down to Earth, thinking more about things like springs, where if I were to extend masses from the spring and pluck them up and down, the springs would oscillate back and forth. Slinkies are a good example of springs. Vertical pendulums are good things of things. Things that undergo repetitive periodic motion is what we're thinking about. Periodic, repetitive motion. Something that oscillates or goes back and forth. A pendulum of a grandfather clock is an example of something that oscillates. The hand swings back and forth. As a result, it does the same thing over and over and over again. If you were to say, a trampoline, if you were to drop a mass onto a trampoline or something, they would undergo oscillations. It would come down, then it would have a restoring force. It would come back up. We saw with boxes attached to springs that they kind of bounced back and forth. There's a lot of repetitive motion that occurs in nature. Oscillations and simple harmonic motion, which is where we're going for with this, really appears everywhere. Guitar strings are a nice example of a very simple idea of oscillations. You pluck a guitar string, it oscillates and does the same thing over and over and over again. That oscillation, that repetition, creates a sound wave as a result. And the rate at which the guitar string oscillates, how much it varies, bounces around, determines the kind of note that you hear. Clocks, both analog and digital, are examples of oscillating systems. They do the same thing over and over again. The hands of an analog clock repeat themselves. They do the same thing again and again. With digital clocks, usually the way that digital clocks, or some of the finest digital clocks, keep time is through oscillations of atoms inside their chamber. The way we define the second is because of the vibrational frequencies of very particular atoms that do it, that oscillate in a way where it does it the same thing over and over and over and over again. Repetitive motion. How your cell phone works, and particularly with old school antennas, when you had that big antenna you had to stretch out, what was happening there? Essentially, the way that radio waves are sent out from your phone is that you have electrons in the antenna that oscillate up and down and create radio waves as a result. The electrons undergo periodic motion, and that creates a radio wave. That's more of a physics 3 thing, but it's the same sort of concept, repetitive motion. Similar idea with how radios work. And all of these examples, notice, are leading to examples of something like wave motion, which wave motion is its own beast that's worth exploring, and we will explore it a little bit after we do oscillations. Because waves are interesting. Apologies for the Shutterstock, but this movie, I think, conveyed it the best. Wave motion, which intuitively, the first example that might come to mind is water waves, waves on the ocean. Wave motion can be very interesting because wave motion clearly allows for energy and momentum. It allows for stuff to be transferred along the wave without the actual object moving that much. Take an example of a slinky. You have a slinky, and you and a friend are holding it, and you shake it up and down. As a result, that creates ripples that go down towards your friend. But the slinky material itself is not moving down towards your friend. The slinky material is staying exactly where it is. It's just going up and down. But yet there's clearly this wave phenomenon, this big bump that is being sent down the slinky. And with it, it carries energy and momentum. So wave motion can have the transfer of energy without the object really actually moving. It's the same idea with water waves. I like this example particularly because of the bubbles. If you focus on a particular bubble, clearly there are waves that are moving across the screen, but each individual bubble is not flying across the screen. Each individual bubble is more or less staying in the same spot and is just kind of bouncing up and down. Yet clearly, if you were on one side of this water wave, and this were a large water wave, you clearly would feel a push. You would feel some momentum. You would feel, work could be done. You would get a sense of all that kinetic energy that the water wave has, even though individual water particles or molecules are not actually going anywhere. They're just bouncing up and down. Yet something is clearly traveling from left to right in this case. So that's what we want to explore with oscillations and working towards wave motion. Let's start with kind of the simplest example that I can imagine that could create some oscillations, which is a vertical mass attached to a spring. So you can imagine I have some sort of spring, and I attach to it a mass that has some mass m. And the spring perhaps has some spring constant k. I could set this up very carefully. I don't actually want to do this video yet. I could set this mass up very carefully. Such that it doesn't move, like this. In this case, it was set up. There is no motion that's going on. Going back to my drawing, what's going on here? In that case, there is a balance if there's no motion, if v equals 0. There is a force that's pulling down on the mass, with force mg, and there is a spring force that's pulling up on the mass with some spring force equal to k times x, where x is the amount of distance it's either stretched or compressed. And it would rest, in that case, if I were to set it up like that, it would rest in some sort of equilibrium. But you could imagine if I were to pull, oh dear God, third time's a charm. If I were to pull down on the object and then let go, motion ensues. In this case, periodic motion occurs as a result. In this case, I set it off away from that equilibrium position, which is what I'm drawing here with this big red line. So when I pulled it down a little bit, I didn't change the mass. I didn't change the mass of the system. But I did stretch the spring a little bit more as a result. And going back to my drawing, I stretched the spring more as a result. So in that case, at that position, there's still the same mg pulling down, but there's a larger kx that is pointing up because I've increased the amount of stretch. There's more force pulling up than there was originally. So unsurprisingly, as a result, when I let go, it initially moves back up and then starts to oscillate around. It oscillates around because notice it does not stop right back at the red line. it actually goes up above the red line. The spring becomes compressed a little bit. Or at least more compressed than it was when it was just hanging vertically. So in that case, the spring force, X, gets smaller. There's less of a spring force pulling up, but there's still the same mg that it's pulling down. So as a result, then gravity wins once it's above that line, and then the object starts to move back down. It passes that horizontal line, the spring force starts to win over gravity, and then the object gets pulled back up. And then gravity wins and it gets pulled back down. And then it just repeats this motion over and over and over again and undergoes oscillations. In this case, very perfect, nice, repetitive oscillation. Then I add more mass to the system, but that's a different question. So if I were to draw this in as a series of snapshots, I could imagine that first the mass might be located here, and suppose this is the equilibrium position. This is the location where if I set it up, gravity has pulled the box down enough so the spring is now stretched a little bit, so the spring is pulling back up. But if I keep it perfectly centered right here, everything is nicely in balance, and it will just stay there. But now imagine I do what I did in the movie, where I start it instead slightly below. Let me see. So in this case, I'm releasing it from rest right down here at this lower point. And the idea here is I want to identify the direction of the acceleration and the velocity at every point to try to get a sense of what's going on. So that I can make a plot of position, velocity, and acceleration for this oscillating bob. So I will get the plot at the ready. So I'm looking at the position. What should we call the position? I guess we could call it y, since this is all vertical. I'm going to look at the velocity, and I'm also going to look at the acceleration, and I'll draw them in different colors. So at this initial point, I'm starting the velocity at 0, so I'll draw a big dot here. The position is at some initially negative value, so I'll put a dot there. And the acceleration, which, again, for all of this, we'll define up as positive. The acceleration when it's down there is that I've stretched the spring more, so there's more of an upward pull by the spring than there is by gravity. So it's feeling some positive acceleration at this initial point right when I let go. Because of that positive acceleration, the object starts to move upwards. Eventually, it gets to this point here and has moved up. We know actually in reality, though, just by looking at the movie, we know it's not going to stop there. We know that once I let go, it's going to reach that equilibrium point and then keep going a bit. And we can see why that has to be the case. All right, so now its position is 0. Its velocity is clearly moving upwards. It's moving up and it's going to overshoot. But since this was the equilibrium position, it's right at this point where the acceleration is 0. Even though the object is moving, it's right at that point where the spring and gravity are nice and balanced with one another. So then I might say, okay, now the acceleration has gone to 0 at the second point. The velocity has gone up to some positive number. And also the position has gone up to 0 at the second point. Eventually it reaches some highest height and comes to rest. It doesn't keep going up forever. eventually it does come to rest, at some vertical height, some maximum height that's reached where it stops and then it turns around. So in that case, the position is positive. It's above this equilibrium point. If we, again, we're calling this equilibrium point 0. We said that that's the highest point where it's about to turn around. The velocity is 0. And the acceleration is less than 0 in this case. The spring is not as compressed anymore. Gravity has not changed. Gravity is now winning over the less compressed spring. So at point 3, now it's positive position, 0 velocity, negative acceleration. It then returns back to the equilibrium point. Y is 0. The velocity is now negative. It's moving downward. And it's back at that equilibrium point, so the acceleration is back to being 0. So again, acceleration is now 0, as is the position. The velocity is now changed to some negative number. And then it finally gets back to where it started. Now it gets back to this point where y is negative. V, it's back down to 0. It's at its lowest point. And the acceleration is back to being positive again. So at this final point, I would say positive acceleration, 0 velocity, negative position. Now I did it at 5, particular points. I could have done this with a much finer, number of snapshots. There's a movie actually that shows this, just for the position. But nonetheless, gives you the right idea. So the idea is that there's this spray can that's attached to springs. They're going to make the spray can oscillate up and down while they pull the cardboard paper out to the right. So essentially the spray can is going to be painting the location that it resides on the piece of cardboard. In this case, you see the height is moving up and down. You might say, that looks fairly sinusoidal or cosine-like. And you'd be right. If I were to do this with many, many snapshots, what I would see is that the position would come up, it would taper off, it would go back down, and then get back to where it started. It would look something like this. The velocity would start by going up, reach some maximum point, start to come down, reach some lowest point, come back up. The acceleration would start at the top, would come back it would come down, keep going, turn around, and then come back up, like that. This is an element of periodic motion, particularly oscillatory motion, motion that repeats itself over and over and over again. And what we will see is that we can actually write down y of t, if I were to just look at the height, we will see that I can write it down as some constant a times cosine of omega t plus something we call the phase angle. So I'll define these and then we'll call it a day. So this is called the amplitude of the wave or of the oscillation. This is, again, some sort of angular velocity, a sense of how frequently it is oscillating. When you're dealing with oscillatory motion, sometimes it's just called the angular frequency. And I will likely use that notation, but it is the same thing as angular velocity in a sense. And then this is called the phase angle. And this is a function of time. This is just cosine. If I were to plot this as a function of time, it would oscillate up and down. So we'll see where this originates and how this connects to actual physics, like spring constants, masses, that sort of thing in the next lecture.